Good morning, ladies and gentlemen. This is the 5th week of our academic semester. The situation is still not all right. The classroom must be empty. So again, I will try to give you a video seminar with examples necessary for the topics of the 5th week of the academic semester. If you remember, on last seminar we finished with example 4.4, linear regression method, linear regression model. We estimated the parameters of this model manually according to formulas. So today we will use more Microsoft Excel, because in Excel we have add-in a lot of functions and we will estimate parameters of regression model in Excel. So please prepare your examples. We will continue with example 4.5. We have a data set in the table below. There are written the annual costs on maintenance. The units are in thousands Norwegian crowns, and the price of the house. There is idea. If you have a house, a large house with a lot of windows, with stairs, with a lot of doors, yes, a really large house, you need a lot of money for the maintenance of this house, yeah, because the house is large, and large house is really expensive house, yeah, large house with a lot of windows, with stairs, a lot of floors, with a lot of doors, etc. If you have small house, yes, you need less money for the maintenance, and the small house is cheaper, probably. Yes, probably cheaper than the large house. So we have here two variables: price of house in million Norwegian crowns and costs of the maintenance of this house. Yes. In thousands Norwegian crowns, and we would like to describe the dependence of costs on the price by the regression line. So I will use the table. I will try to draw a chart for you, and we will imagine the situation. Yes, there you have two variables. Variable y, dependent variable, and variable x, independent variable. Yes, and we would like to describe this dependence. Yes, the firstly by chart, and after by two parameters: intercept and slope of the regression line. You can see that we have here decimals. So it will not be easy to do this manually on the calculator. So we know that the chart has two axes. There is x, there is y, yes, and we can use, for example, scatter plot with these points. Yes, and we will see the dependence. Yes, and there is possible to use regression line. Regression line y is equal to beta 0 plus beta 1 x, and that's all. I will check your formulas. In your formulas, Mr. Helma using b instead of beta. Yes, in literature you can find betas, but in our formulas we have b0 plus b1x. On last seminar we estimated b0 intercept, yes, intercept, and slope, yes, slope of the regression line. Okay, so we will use Excel. We will try to draw this chart, and after we will estimate the parameters b0 and b1 of this regression line. So if you have English version of Microsoft Excel, you can check the data leaf. Yes, the data leaf. In the top part of this window, there is a data leaf. Data. Now please wait a second for the screen. Okay, data leaf, yes. On the right side, you have nothing, it's empty. So please, you can click on File button, yes, File button here, left top corner of this window, File button, and on the bottom there you have Options, yes, Options button. So please click on Options. And there you have add-ins. Yes, please check this column, add-ins. So please click on this add-ins, and on the bottom there you have manage Excel add-ins, and there is Go button with 3 dots. So please click on this Go button with 3 dots and select Analysis Toolpath. Yes, Analysis Toolpath, select, and click on OK. OK. And we have data analysis here, yeah? The data leaf data, and data analysis in the right top corner. Okay. So first the chart. Yes. We can select these two variables. Yes. Variable y, variable x, two columns. There is insert button, leave insert, yes, insert, and we have here charts, a lot of charts, yes, and there you can see insert scatter, x, y, or bubble chart, yes. The first letter is X, so probably it will be better to change the order of these columns. Yes, so I will change the order of this column, X and Y. Yes, X variable, Y variable, insert button, charts, scatter. Okay, yes, this is scatter plot, variable X and variable Y, yes, variable X, variable Y. Dependent variable costs on maintenance, and independent variable price of the house, yes. And if you check these points, you can see, yes, the dependence. If you have a larger house, yes, more expensive house, you need more money for the maintenance. Yes, and we are able to estimate the line, two parameters B0, B1, and create this line. So we can move this chart, yes, we can move this chart, for example, here on the right side, and now we will estimate the parameters. So please use the data leaf, yes, data leaf. And here we have data analysis, so select data analysis, and in this table we will find regression. Yeah? There you have a lot of tools, analysis tools, so we will find regression. Okay, and in this table we have input y range and input x range. Variable y is in this course only one. Yes, we will analyze in our seminar only one dependent variable. Yes, because at the time in this course we have only one equation model. independent variables, x, yes, explanatory variables. We have one variable, but we can have more variables, yes? So input x range, there we can use more columns, but we have only one variable x, yes? So we will select the data input y range and input x range. Input y range, I will select column y, yes? Input y range, input regression, input y range, this column. I selected also the label, yes? Also the label, so this column, input x range, input x range, this column also with the label. I will select labels, yes, because I selected labels in this column. Also the first cell, yes, in this column. Okay, that's all, yes. That's all. You can click on OK and you will see this output. I will zoom this output and we will find what is necessary for us. Yes, what is necessary for us. So please wait a second. I will zoom this document. This is not necessary. Coefficients. I will use only 2 decimals, yes? It will be more comfortable for us. So only 2 decimals. And 4 decimals here in regression statistics. Okay, there is a lot of values, a lot of numbers, yes? We are at the beginning of the semester, so we don't know what is written here, but we can find coefficients. Yes, there is a table with regression coefficients, and we will use these 2 coefficients, intercept and variable x. So we have here intercept and slope of the regression line. It's possible to rewrite these values on the table. So again, please wait a second. I will use table and we will write the formula, yes, the equation of this regression line. Y is equal to minus 161 minus 161.68 plus 7.58x. 7.58x. So this is regression line, yes? There is B0, there is B1, these 2 coefficients. In our example, was written a described dependence, of course, to the price by the regression line. We estimated this regression line, and also we used the chart, yes? There is our chart with data. Okay. What else? Assess the quality of the model by the coefficient of determination. On the previous seminar, we calculated coefficient of determination R squared. We will open formulas. Where we have formulas here. R squared, according to Mr. Hellman, we have in denominator sum of squares regression. In denominator, there we have sum of squares total. So sum of squares regression divided by sum of squares total. Okay, in our output Microsoft Excel, summary output. Yes, can you see this table? I will check if you are able to see this table. Yes, probably yes. Summary statistics. That is R square. Yes, R square calculated 0.9704. Okay. 0.9704. Okay, so Microsoft Excel calculated R square for us. We know that R square is from range 0 and 1. Yes, and this R square is close to 1. There is strong dependence, yes, between variable x and y. A lot of data, a lot of variability, yes, is explained by this model, because in the numerator there is regression, sum of squares, regression variance, explained variance. In denominator there is a total variance, yes, and if this variance is close to total variance, yes, this value limit to 1. Yes? The more variance, the more variability of data, yes, is explained by this model. And in this table, yes, in this output, you have 3 tables. The first regression statistics, ANOVA table, and the table is coefficients. You can check the words, yes, these 2 words in ANOVA table, regression and residual. Yes, can you see these 2 words? I will use also the screen, so please wait a second for the screen. Okay, the screen is ready. Again, I will use only 2 decimals in this ANOVA table, and I will check these 3 values. Yes, there is written regression, residual, and total. Mr. Hellman informed us. In the case of calculation of sum of squares, SS, using total, regression, and error. Error means residual in this situation, in this case. So I can write here residual. This is a synonym of the word error. Yes, error. So regression, error, and total, and this SS, this means sum of squares. Yes, sum of squares. Sum of squares. Okay. Okay. So we have here 3 sum of squares. R square. We already used this R square. Yes. Do you know what is it multiple R in this table? In this table of regression statistics, this is correlation coefficient. Yes. At home, you can try manually calculate correlation coefficient. This is classical Pearson correlation coefficient. Correlation coefficient. Yes. Do you remember example about squats and push-ups? Yes. We calculated the correlation between 2 variables. Yes, and there is correlation coefficient very close to 1. Yes, you know that correlation coefficient is from range -1 plus 1. Yes, if correlation coefficient is close to +1, there is strong correlation, dependence, positive dependence between variable x and variable y. Yes, so there is really strong correlation, strong dependence. R square we have calculated by Excel, but we can verify if this R square is calculated correctly, because there we have sum of squares. So we will use these sum of squares. This ratio, regression 8810, 8810.24 divided by total sum of squares 90, 78, 67. 86. Okay, so 881015.24 divided by 907867.86, 0.9704. So you can see that this is equal as sum of squares. Okay, what else? So we describe the dependence of cost of the price by the regression line. We have B0, B1. Assess the quality of the model by the coefficient of determination. We found coefficient of determination is very close to 1. Determine what average increase of the annual costs corresponds, according to this model, to increasing of price by 1 million Norwegian crowns. So I will clean the whiteboard. There is our regression line, and we will calculate estimate, the point estimate. Yes, the point estimate. We will use this model for estimation. What average increase of annual cost corresponds, according to this model, to increasing of price by 1 million Norwegian crowns. So costs are in thousands, yes. Costs on maintenance are in thousands, and price is in millions. So the price is in millions. Okay, so what is it? 7.58. This is regression coefficient B1, yes, times 1 million, yes, instead of X, there is 1 million. So result is 7,580 Norwegian crowns, yes, Norwegian crowns. Okay, so average increase of the annual costs. What average increase of annual costs corresponds, according to this model, to increasing of price by 1 million Norwegian crowns. If the price will be higher, yes, by 1 million Norwegian crowns, yes, you need more money for maintenance, more by 7.58 thousands, yes, so 7,580 Norwegian crowns. So it's a value of this regression coefficient, interpretation of this regression coefficient. Estimate the amount of the costs when the price of the house is 80 million Norwegian crowns. So y is equal to minus 161.68 plus 7.58 times 80. Yes, we know that this is in millions. This is in millions. Okay, so 7.58 times 80 minus 161.68. 444.72 thousands. Yes, so 444 thousands 720 Norwegian crowns. Yes, this is result. So if you have house, yes, with price 80 million Norwegian crowns, yes, you can expect that you need every year, yes, for maintenance of this large and expensive house, yes, you need 444,720 Norwegian crowns. So this is estimate of costs. Okay, and finally we can again use Microsoft Excel one more time. So please wait for the screen. Okay, the screen is ready. There is our chart. So I will show to you again our chart. Okay, and it's possible to use right button. Yes, use right button. Click on, for example, this blue point. Yes, right button on this blue point. And there we have at trend line. Yes, at trend line is 3 dots. So please, you can click on this button at trend line, and here on the right side, yes, you have trend line options. And we know that we used linear function. Yes. So you can see that we have trend line options: exponential, linear, logarithmic, polynomial, power, moving average, yes, etc. A lot of options. So we will use linear. There we can select display equation on chart and display R² value on chart. So these two options, yes, you can select. You can select these two options: display equation on chart and display R² value on chart. Okay, I will close this. I will use 20 points. Okay, here 20 points. Okay, here 20 points. This is a little bit more visible for you. So our regression function y is equal to b0 is this one, minus 161.68. This is b0 because there is no x and there is x. So this is the slope of the regression line, 7.5819, yes, 4 decimals. And R² is here 0.9704. So you are able to see this dependence, yes, dependence of the price of the house on the costs on maintenance, yes. Okay, so this is a descriptive way, yes, descriptive part of the regression analysis. We can continue with example 5.1, yes. So again, we'll continue with regression models, but now this will be a little bit different. It was analyze the amount of yield. Yes, so our dependent variable will be amount of yield, variable y, independence on the amount of used fertilizers. Yes. The data set is written in this table below. And we would like to fit the data by quadratic regression function. Quadratic regression function in different literature, this is called regression parabola. Yes, quadratic regression function, and compare the results with regression line. So in the previous case, we had regression line. Yes, y is equal to b0 plus b1x. So this was regression line. If we check the formulas, yes, formulas, wait a second, quadratic regression function, y is equal to b0 plus b1x plus b2x squared. Yes, so this is quadratic regression function, regression parabola. Regression line is here. Yes, variable x, variable y, and quadratic regression function. For example, this one, yes, variable y, variable x. So we need data, yes, we need variable y, variable x, and variable x squared, yes, column, yes, so 3 columns with data. Okay. For linear regression, for line, yes, we need y and x, yes, only 2 columns, yes, only 2 columns with data. Okay, so our duty is clear: fit the data by quadratic regression function, regression parabola, and compare the results with regression line. We have transposed the data, yes, from the rows to columns here. So we will use this data set, yes, and we will estimate the parameters of these two functions. We are able, yes, to estimate b0 and b1 manually. Yes, this is possible according to formulas. Yes. Manually, but for regression parabola, quadratic regression function, we don't have formulas in our formula sheet. Yes, it is possible to estimate this manually. Yes, I am able to do this. I know these formulas, but you don't have these formulas written in your PDF file, so we must use Excel. Yes. So it's possible to estimate the coefficients of regression line manually, yes, but for regression parabola we need Excel because of lack of formula in our formula sheet. So we will use Microsoft Excel. You know that we need 3 columns of data for regression parabola, quadratic regression function, and 2 columns for regression line. Yes? I will zoom this document and I will check if you are able to see data. Probably yes. So we have here variable y, variable x, and for parabola we need second power of variable x. So for example here x squared, yes, x squared, format cells, superscript, okay. So there is third column, equal sign, yes, x, power function, left out, and combination 9, 4, yes, left out, 9, 4, and there is this hat, the second power, the power, the power function powered by 2, and you will see second power of variable x, yes. So we have here the data. You have installed @in, yes, @in on the data leaf. So please click on data leaf and in the right top corner you have data analysis. Yes, data analysis. Okay, regression analysis tools, regression. Okay, I will delete these ranges. Yes, and I will scroll down where we have our data set. Yes, so input y range and input x range. Yes? There is our table with the data. So I will select this first column, like variable y. Yes, also with the label. Yes, also with label. So input y range, this column. Yes, and input x range, these two columns. Yes, x and x squared, because firstly we will calculate quadratic function. I have selected labels, yes, labels, and that's all. You can click on OK, and you will see this result. I will zoom this document, and I will use only 4 decimal positions, and here in this table 2 decimal positions. Yes, this is not necessary. Okay, okay, okay. And only 2 decimals here. Yes. So this is regression parabola, quadratic regression function. I will check if you are able to see the values. Okay, I hope yes. I will rewrite these values on the whiteboard. Yes, what is necessary for us? Coefficients. Yes, coefficients of this quadratic regression function here. Probably we will use correlation coefficient r squared, and since this time, we will use adjusted r squared for comparison of different models. Yes, so these 3 values. Maybe we can verify if everything is calculated correctly by sum of squares. Yes, there is our ANOVA table. Regression variability, residual variability. We can write here the word error. Yes, error and total. Yes. And this SS means sum of squares. Sum of squares. Yes, so you can see regression, error, and total sum of squares. Yes, so we know we are able to use these yellow values. Yes, and we'll estimate also the regression line. Yes, so please one more time open sheet 1. Yes, and we will use one more time regression analysis. So please click on data leaf, data analysis, regression. Yes, okay. Input y range is still the same. Yes, this column. And input x range, independent variable, is only one column x. Yes, so please change input x range. I will delete this, and I will select this column. Yes, x and the data. We are using labels. Yes, so you can click on OK. The least squares method will provide the results. Again, I will use only 4 decimals here in summary statistics, and 2 decimals in other tables. Okay, please wait a second. Okay, 2 decimals here. I will zoom this document, and I will check if you are able to see the values. Yes, wait a second, I will check. I hope that everything is all right. So what is necessary for us? Coefficients, yes? Coefficients here. Sum of squares probably, yes? Sum of squares. These three, yes? Regression, residual, and total. Okay, and these three values. Yeah? There will be correlation coefficient. R squared, and we will talk about adjusted value of R squared. Yes. Okay. So this is quadratic regression, yes, with three coefficients, and linear regression, regression line, with these two coefficients. Okay, so we will use the whiteboard. Can you see regression line and quadratic regression, first and second function? There is output, regression output. You can see two coefficients, yes, intercept and x. So this is the line, yes, intercept and slope. So I will write here y is equal to minus 53.88 minus 53.88 plus 15.40 plus 15.40x. So this is regression line. Quadratic regression needs three coefficients. So another sheet with another output, intercept, x and x squared. Yes. So I will rewrite coefficients. Y is equal to minus 32.22 minus 32.22 plus 7.30 x plus 0.72 x squared. Yes. So this is quadratic regression function, regression parabola. I will check what is necessary to do. Fit the data by quadratic regression function, parabola, and compare the results with regression line. How can we compare results? Yes. How can we compare the results? In the chart, yes, in the chart, or by appropriate coefficients. Yes, there is B. Characterize the tightness of dependence by appropriate index coefficient. We can evaluate the models. Yes, we used R squared. Yes, we used R squared. For the characterization of dependence. But now we have two different models with different number of coefficients, different number of parameters. Yes. So it's necessary to use coefficient for comparison two different models. Coefficient which think about the number of these parameters, these coefficients. In formulas, we can find the adjusted version of R squared, adjusted by degrees of freedom, adjusted by number of coefficients. So I will rewrite this formula on the whiteboard. R squared adjusted is equal to 1 minus, in parentheses, 1 minus R squared, yes, times n minus 1 divided by n minus p. So we'll try to calculate two adjusted values of r squared. In our output, there is, for example, sheet 2, intercept x and x squared. So this is quadratic regression function where we have r squared here, 0.8687. So where is r squared 0.8687? 8687. Yes, and in the case of regression line, so I must find the output with only two coefficients here, intercept and x, r squared 0.8635. 0.8635. Yes, there is r squared. Okay. We will use this formula, yes, and we will calculate or one will be enough, for example, for parabola only, because you can see adjusted r squared is written here. Yeah? So this is the line, and this is the parabola. 0.8031. I will calculate this value, yes? 1 minus in parentheses, 1 minus r squared of parabola, 0.8687. 0.8687, close the parentheses, times n minus 1, number of observation. Number of observation 7. Yes, 7 values. Yes, we had 7 values. 7 minus 1 divided by n, 7 values, 7 observations, minus p, number of parameters, number of b in our regression model. 1, 2, 3. Yes, b0, b1, b2, 3 b's. So minus 3. I will use a calculator, yes, and I will verify that this adjusted r squared is calculated correctly. So 1 minus 0.8687 times 6 divided by 4. 6 divided by 4. 1 minus this value. 0.8031. 0.8031. Yes, so we have adjusted value, adjusted version of r squared. So this is quadratic. And adjusted r squared for the line is 0.8363. 0.8363. Okay, so we can check the situation. R squared is higher in the case of regression parabola, but for evaluation of two models, yes, for evaluation of two models, we're trying to model the same dependent variable y, amount of yield, yes. It's better to use adjusted version of r squared because we don't have the same number of parameters. Yes, there we have 2 parameters, there we have 3 parameters, and this adjusted version adjusted version of R squared, yes, using the number of observation and number of parameters, yes, in this formula for the calculation of this adjusted version. So we must decide, yes, according to adjusted R squared, that line is better model, because line, yes, has higher value of adjusted R squared. If you use this simple version, you can see that there is higher in the case of parabola, but parabola has three coefficients. Yes, there is penalization in this calculation, and line is probably better because line has higher adjusted value of R squared. Yes. Okay, can you see the screen? There is column X, there is column Y. Scatter plot, yes, is named XY scatter plot. So on the first position, copy, paste, yes, I need to put this column X, and on the second position, copy and paste, I will put the column Y, yes, and now simple scatter plot. So we will select the data, column X, column Y, there is insert button, yes, insert button, and there you have a lot of charts, and there you can see insert, scatter, XY or bubble chart. So we'll use scatter plot. This simple scatter plot, yes. Variable Y, dependent variable amount of yield, yes. So there is variable amount of yield, and there we have used fertilizer, yes, in kilograms probably. Amount of yield in cubic meters, and used fertilizers. And there is the dependence, yes. We estimated regression line, and we also estimated quadratic regression. According to the structure of this data, yes, you can see maybe the dependence is linear, maybe it looks like saturation S-curve, yes, but in your formulas and in this course we are not talking about this type of function, saturation S-curve, yes. Can you imagine exponential increasing, yes, and there the changing point, yes, to parabolic trend and decreasing, but we have now only available line and parabola, so use right button, yes, right button, and there you can find add trend line, yes, add trend line, and the first option is linear, yes, first option, which is here, or second, there's exponential, second is linear, but we will select linear, and again, we will display equation on chart, yes, and we will display R squared value on chart. We know that for comparison of different models with different number of coefficients, we must use adjusted version of R squared. There is not option as adjusted R squared. There is only the simple value, simple R squared. Display equation on chart, display R squared on chart. So this is first chart, and I will create another one. Yes, I will create another one. So again, the data set X and Y, insert charts, yes, and scatter plot. This is the same chart, yes. It's the same chart. So wait a second. Okay. Okay. Yes, can you see? There's a line. There we have data only. I will use right button. Yes, I will use right button at trend line. And there is polynomial. Polynomial, yes, polynomial. And I will use order. Okay, can you see these two charts on the screen? So there is the line, and there we have data only. So again, I will use right button, yes, on any of these blue points, right button, and at trend line, yes, at trend line. No linear, yes, because linear is in the right chart. I will use polynomial, yes, because quadratic regression function parabola, yes, is the polynomial of the second order, yes, polynomial order 2, polynomial of second order, because there is x and x squared, yes. So this is polynomial type. Polynomial trend line, so polynomial order 2. I will use display equation on chart and display r squared value on chart. So this is parabola. According to Mr. Hellman presentation, quadratic regression, yes? Quadratic regression function, and here we have line, yes, regression line. I will use 10 points size of values, yes, okay, 10 points, 10 points and 10 points. Okay, so amount of yield, yes. Maybe you can see there is a range from 0 to 80, there is a range from 0 to 70. I will use right button format axis. Yes, I will set maximum 80 because it's better to have the same measure, yes, the same measure, the same range in all charts. So, regression parabola, quadratic regression, polynomial of the second order. You can see minus 32.22, this is B0, yes, 7.29, 7.30, this is B1, and 0.72 is B2. You can check coefficients from this sheet, yes. Intercept minus 32.22 plus 7.30x plus 0.72x squared, yes. So this is the parabola, and there is the line minus 53.88 plus 15.40x. Okay, 15.40x, yes, so there is B1 minus 53.89. There is B0. We can see only r squared, yes, you can see that this r squared is higher, but we know that this r squared mustn't be used for the evaluation of these models because we have 3 and 2 coefficients, 3 and 2 parameters. So we must recalculate this r squared to adjusted r squared, or we must use summary statistics and find appropriate coefficient adjusted r squared in summary statistics. And we can finish this example. We can calculate a point estimate of the amount of yield when 8 kilograms of the fertilizer was used. We can try to estimate this amount using regression line and regression parabola, but we know that regression line, according to evaluation, according to adjusted r squared, is better model, yes, statistically better model. So the correct estimate will be from regression line, but we can calculate these estimates both for line and for parabola. So please wait a second, I will clean the whiteboard. Okay, so regression line, better model, yes? Y is equal to minus 53.88 plus 15.40 times 8 kilograms of fertilizer, yes? And wrong model for this situation with lower value of adjusted r squared, regression parabola, quadratic regression function, y is equal to minus 32.22 plus 7.30 times 8 plus 0.72 times 8 squared. Okay, we can use calculator. Minus 53.88 plus 15.4 times 8. 69.32 cubic meters. Yes, cubic meters of yield, yes, this is amount of yield, estimated amount of yield. And here, minus 32.22 plus 7.3 times 8 plus 0.72 times 8 squared. 72.26 cubic meters. Yes, so you have here two estimates, yes. This one is probably better, yes, because this estimate is calculated on the basis of a better model, statistically better model, yes, with higher adjusted value of r squared. This one is a little bit more optimistic, yes, but this optimism may be mistake, yes, because this model is weaker, yes. This one is stronger with higher value of adjusted r squared. This is a little bit more weak. Okay, so that's all. We fitted the data, we characterized the tightness of dependence, and we calculated 2-point estimates. Point estimate of the amount of yield when 8 kilograms of the fertilizer was used. So we can continue. So example 5.2, there is given the output from the regression analysis. on the dependence of dependent variable y on the independent variable x. We will try to fill in missing data, we will try to interpret results. What can you see? There is a table with analysis of variance. We know this table analysis of variance. You know this table from presentation of Mr. Hellman, and you already seen this table today. Yes, if you check, for example, there is previous example. This is regression line. Yes, because you can see there we have two coefficients, intercept and slope, and there is ANOVA table. Yes. We identified here in this ANOVA table sum of squares. Yes, first one, second one, third one. Regression, sum of squares. Residual, it means error, sum of squares. Yes, residual, so this is error, sum of squares, and total, sum of squares. And now there is again ANOVA table. You can see source, between group, variability, within group, variability, and total variability. We know that the first row, yes, first row is regression model source of variability. So I can write here that between group, this is equal to regression. Yes, regression. Wait a second. I will use wider column. Yes, regression. Between group, it means in this situation, regression. Within group, yes, within group, we know that on the second row in this ANOVA table, we can find error source. Yes, error source of variability. So within group is equal to error, and the total is total. Yes. What can we find here? DF, degrees of freedom. This will be topic of seminar 11. Other statistics, also the topic of week 11, according to presentation of Mr. Hellman. And you can see that we have here sum of squares. Two cells are empty. We know total sum of squares. Yes, and we have here two important statistics, evaluation statistics: R squared and adjusted value of R squared. Yes, so we can open formulas now, where we have formulas here, and we know that R squared is calculated like ratio. Yes, so regression sum of squares and total sum of squares. We know total sum of squares, we know R squared, so we are able to calculate regression sum of squares. So please wait a second. We will use the screen and we will calculate. Missing sum of squares. Okay, so are you able to see the values? R squared, yes, R squared is 0.4835. 0.4835. Sum of squares total is equal to 42716. 42716. I know that R squared is calculated like sum of squares. Regression divided by sum of squares total. So sum of squares regression is calculated like R squared 0.4835 times total sum of squares 42,716. Okay. So 0.4835 times 42,716. 20,000. 653.186. So this is regression sum of squares. We know that sum of squares total can be calculated like sum of squares regression plus sum of squares error. Okay, so error sum of squares, error is calculated like sum of squares total minus sum of squares regression. So 42,716 minus 20,653.186. Okay, 42,716 minus this value 22,062.814. Okay, so regression sum of squares, error sum of squares, total sum of squares are squared, yes, and what else can we find in this regression analysis output? Parameter estimates, yes. You can see intercept and variable x. So this is the line. Yes, this is classical linear regression function. Yes, regression line. So we will rewrite the coefficients. This regression line y is equal to b0 plus b1x. Yes, this is classical regression line. So y is equal to intercept minus 67062 plus 211x. Yeah, so this is regression line with intercept and slope. Slope is positive, yes, plus sign, so the line will be increasing, yes, increasing function, increasing regression line. So there is given output from regression analysis, filling missing data, so we calculated unknown sum of squares. The other statistics with the topic issue of week 11. We interpret values, we try to interpret values, yes, and that's all. There is no other duty for us. Okay, example 5.3. You are selling CDs, yes? Assessing the influence of two different types of advertisement on sales of new CD, we obtain the following data. So you are selling CDs, you want to sell a lot of CDs, so you need advertisement. You can invest, yes, you can invest on advertisement in radio and television, and you can invest on advertisement in press. So we would like to estimate the parameters of this regression plane. So we need to estimate B0, B1 and B2. Yes, three coefficients. Again, we will use least squares method. Yes, method of least squares method. I am able to estimate these three coefficients manually, yes? I know the formulas, but you don't have these formulas in your formula sheet, so we must use Excel. Yes, we will use Microsoft Excel, regression analysis in Microsoft Excel, and we will estimate parameters of this regression plane. Yes, regression with two explanatory variables. So please wait a second. I will prepare the screen. Yes. I will check if you are able to see the screen. And I will zoom this document a little bit more, yes? Okay, so there is the data set, yes? Variable, variable y, variable x1, variable x2. Because today we already installed analysis tool pack, yes? If you click on data leaf, yes, data leaf, you have data analysis here in the right top corner. So you can switch on this data analysis and please find regression. Yes, regression. Analysis tools, regression. Okay. I will delete this input y range and I will delete this input y range. Yes, I will scroll down. I will scroll down and I will find my data set. Okay. Input y range. This column. Now I will not select the labels because can you see the row 56 and 57? I have here merged cells. Yes. So this will be a mistake, yes, mistake for Excel. So now I will not use labels and I will select only the numbers, the values, yes. So please select input y range, the values from 1119, yes, to value 1717, only these values, yes. And input x range, these two columns, yes, these two columns, again without labels, yes. I know that first column is radio and television, advertisement in radio and television, and the second column advertisement in press, yes. So I don't have selected labels, and that's all, yes. You can click on OK, and the least squares method will estimate results. So I will zoom this document. I will use only 4 decimals here. Okay, also less decimals here. I think that 2 will be enough. Okay, are you able to see these results? Probably yes. So what is important for us? Coefficients, yes. Coefficients, and we know that x variable y, there I have radio and television, radio and TV, yes, radio and television, and this second row, x variable 2, press, yes, advertisement in press. Okay, so coefficients. Maybe we will use for something sum of squares. Yes. You can see regression, residual, it means error. Yes, residual. We know that this means error and total, sum of squares. Sum of squares. Okay, sum of squares. And other important characteristics, this multiple R is correlation coefficient. Correlation coefficient, you can see 91, yes, 0.91, so it's close to 1, plus 1, so positive dependence. If you invest more money, yes, if you invest more money for advertisement, you can expect more sales, yes, more sales of your new CD. R squared and adjusted R squared. So these three characteristics are also important for us. Okay, what is written here? Estimate the parameters of regression plane. It is describing the dependence of sales on the amount of costs on advertisement in radio and television, variable x1, and on the amount of costs on advertisement in press, x2. Characterize the strength of the dependence. This is only one model, yes? Regression plane. So we can use simple R squared, yes? We don't have to use adjusted R squared because we have here only one type of model, yes? We are not comparing this model with other one, so the strength of the dependence, correlation coefficient or R squared, yes, it's enough for us. So wait a second and I will rewrite this regression plane on the whiteboard. Okay, so this is the sheet with outputs, yes, with three output tables. I will use these coefficients. Variable y is equal to 123.70. 123.70, this is intercept, plus 12.64 x1 plus 18.86 x2. This is regression plane, yes? Regression plane. We know that this variable x1, advertisement in radio and television, yes? Radio plus TV, and there we have press. And because we are not comparing this model with another one, yes, we can use for evaluation of this model correlation coefficient or R squared, yes. Correlation coefficient, Pearson correlation coefficient according to your formulas. RYX, yes, RYX is equal to 0.9124, and R squared is equal to 0.8324. 8324. This is correlation coefficient. You are able to calculate second power, yes, of this correlation coefficient. Try to use your calculator. RYX, yes, 0.9124 and second power, yes, powered by 2. Calculate this in calculator and the result is 0.8324. 8324. So second power, yes, of correlation coefficient is classical simple R squared. Yes, so you can see that there is some mutual dependence between correlation coefficient and R squared. Yes, so we can choose either correlation coefficient or R squared for evaluation of the model. Yes, we will receive the same information, the same amount of information, because we are able to calculate R squared if we know correlation coefficient, and we are able to calculate correlation coefficient if we know R squared, yes, because there is the dependence. Okay, what else? In this, we estimated the parameters, we characterized the strength of the dependence, yes. What average increase of sales can be expected according to this model when the cost on advertisement in press increased by 5,000 Czech crowns, while the costs on advertisement in radio and television stay constant. So this is, there we have costs in thousands, yes. And sales are also in thousands, so there we have thousands, yes, units. Important for us are units. Thousands, yes, and here also thousands. Okay, what average increase? When the cost on advertisement in press increased by 5,000 Czech crowns. This stay the same, so 18.86 multiplied by 5,000, yes, the result 18.86 times 5, result 94.3 thousands, yes, so this is 94,300 Czech crowns, yes. So if you invest more money for advertisement in press, yes, more by 5,000 Czech crowns. Yes, I don't know what can you buy if you pay 5,000. Yes, small advertisement in some journal, yes, or newspapers, but a lot of people will see this advertisement, yes, people buy more CDs, yes, and you can expect that your sales will be higher by 94,300 Czech crowns, yes, and we can continue another estimate. Calculate a point estimate of sales when there is spent on advertisement in radio and television 40,000 Czech crowns and on advertisement in press 35,000 Czech crowns. Yes, so we will use this model. So this is our model with coefficients, and I will use this model for the calculation of estimate of sales. Yes, why? Our sales in 1,000 Czech crowns are equal to 123.70 plus 12.64 times 40,000, yes, plus 18.86 times 35,000. Yes, result will be in thousands. So 123.7 plus 12.64 times 40 plus 18.86 times 35. 1289.4, and we know that this is in thousands, so 1,289,400 Czech crowns. Yes. So if you invest, if you invest to advertisement in radio and television, 40,000 Czech crowns. Yes. The people will see this advertisement. If you invest 35,000 Czech crowns, yes, for advertisement in press, yes, people see advertisement and people buy your CDs, you can expect sales, yes, 1,289,400 Czech crowns, yes, you can expect these sales. Okay, that's all. Okay, until this moment, we solved correlation analysis and regression analysis. Yes, the topics, issues from presentation of Mr. Hellman from the 4th week of the academic semester. And now, this is 5th week of academic semester, and we will continue with the 5th presentation. The first topic, the first issue in the 5th presentation is time series, and with this time series we are able to calculate the basic measures of dynamics. Yes. There is example 5.4, calculate elementary characteristics, measures of dynamics of the time series gas production from year 1980 to 1985. So what is it? Time series. Do you remember classical regression line? There we had variable x and there was variable y. Yes. Regression line. We had here observation. Yes. Observation, and we fitted the data by regression line. Yes. Y is equal to b0 plus b1x. Yes? This was classical regression line. And now, instead of variable x, yes, there is a time. Yes, time. Are you able to imagine, for example, the development of some portfolio, the price of portfolio, yes, on the stock market, for example, the development of price, some portfolio in Czech crowns, yes, in the time. This is the time series, yes, and also the development of gas production, yes, from year 1980 to 1985 is time series. Yes, we have here year 1980, 1981, and gas production in cubic meters. Yes, gas production in cubic meters. And we are able to calculate some measures of dynamics. So we will check formulas. Yes, we will check our formulas. And there is a chapter, descriptive analysis, descriptive time series analysis and predictions. And Mr. Hellman using, for example, this formula delta in time t, like the first difference, absolute increase or absolute decrease. Yes. So in this time series, this is variable y in time t. Yes. In our situation, we have six observation. T is equal to 1, 2, to t. Our situation 1, 2 until 6. Yes, because we have years. 1980, 1981, yes, until 1985. Yes, 1981, 1985. Only 6 observations. Yes. So we will use this formula: delta in time t is equal to variable y in time t minus variable y in time t minus 1. Yes. Simple difference. Yes. First differences: absolute increases or absolute decreases. Growth coefficient. Coefficients of growth, k, t, k in time t. K in time t is equal to ratio. Yes? There is difference, there is ratio. Y in time t divided by y in time t minus 1. Yes? So absolute increases, first differences, and growth coefficients. Yes. Okay. So what else? If I check this example, first differences, growth coefficient, mean first difference, and mean growth coefficient. So in your formulas, mean first difference. Where is mean first difference? Will be delta with stripe. Delta mean. Where is delta mean? Here is delta mean. Last observation minus first observation. So delta mean is equal to yn minus y1 divided by n minus 1. N minus 1. So last observation, yes, last observation minus first. Last observation minus first observation divided by n minus 1. In our situation, we know that we have 6 observations, yes, 6 minus 1. So this will be mean first difference, yes, and mean growth coefficient k with stripe, yes. Mean growth coefficient k with stripe. I will delete this chart. K with stripe is equal to, there is a root, n minus 1 root, yes. So in our situation 6 minus 1, yes. N minus 1. So in our situation this will be 6 minus 1, yes, fifth root. From the ratio, last observation divided by first observation, yes. Yn divided by y1. So last divided by first. Yes. So the time series from year 1980 to 1985, yes, 6 years of the development of gas production, and we'll calculate these measures of dynamics, characteristics of dynamics. First differences, growth coefficients, yes, mean first difference, and mean growth coefficient. It will be better to do it in Excel because we have prepared the tables and the cells. Yes. Okay, I hope that you are able to see the screen. Yes, so we will start with calculation of first differences. I cannot start here because you know that first difference delta t is calculated like observation minus previous observation, and I don't have this value from year 1979. So I will lose one observation and I must start here. This observation minus this observation, yes, first difference. Value in time t minus previous value. And interpretation is absolute increase or absolute decrease, yes. If the value is positive, it's increase, absolute increase. Between year 1980 and 1981, yes, the production of gas increased by 77 cubic meters. Between year 1981 and 1982, the production of gas increased by 30 cubic meters. Etc., etc. Yes, you are able to interpret these results between year 1984 and 1985. The production of gas increased by 39 cubic meters. If the value is negative, yes, it means decrease. Yes, between year decrease. This is increase. We can continue with growth coefficient, yes, growth coefficient. Again, we are not allowed to start here because we don't have, observation for year 1979. So we must start here. Equal sign, production, yes, production of gas in year 1981 divided by production of gas, this value, yes, production, not years, yes, it will be mistake, production, yes, value in time t divided by value in time t minus 1, yes, growth coefficient. Result will be relative number, yes, relative number. And if this number will be higher than 1, it is increase, yes. If the value will be below 1, the result will be decrease, yes. So this is relative increase, and you are able to interpret this relative increase in percent. What it means, this 1.06, 6%, yes. Between year 1980 and 1981, production of gas increased by 6%. Between year 1981 and 1982, the production of gas increased by 2.2%. Yes, you are able to multiply this by 100 and interpret in percent. Yes. The largest increase, yes, 102 cubic meters, is between year 1982 and 1983, yes, and this relative increase is 7.3%, yes, 7.3%. This is the largest increase. So, for us differences and growth coefficients, yes, if the value will be, for example, this is example, yes, 0.966, yes. If there will be value 0.966, this will be decrease, yes. Between year decrease, decreasing by 3.4%, 3.4% because it's below 1, yes. But we have increasing every year, yes. And now we can calculate mean first difference, yes. According to this formula, where is delta with stripe, yes. Last observation minus first observation divided by n minus 1, yes. Okay, so mean first difference, equal sign, I will open the parenthesis, numerator. Last observation minus first observation, close the parenthesis, yes? Be careful, every time we must take these values, yes? Production. Last observation minus first observation, divided by n minus 1. 1, 2, 3, 4, 5, 6. 6 minus 1 is 5, yes? Divided by 6 minus 1, divided by 5. So this is mean first difference, 64.8. What it means, how many more gas is produced each year, yes? Every year you produce more gas, yes? More by 64.8 cubic meters, yes? So this is mean first difference, mean average increasing, mean increasing every year, yes? Every year you produce more gas by 64, in average, 64.8 cubic meters. And the mean growth coefficient, yes, we can calculate mean growth coefficient. So we can write equal sign, we can open the parenthesis, and we know that there is a ratio, yes? There is a ratio, last observation and first observation, and there is a root, n minus 1 root. So 6 minus 1, 5, fifth root. We will use power function, and this ratio will be powered by 1 divided by 5, yes? So there is 1610 divided by 1286. I will close the parenthesis. Power function, the hat, yes? Left out 94 on the numerical keyboard, yes? Left out 94, and you will see this head function, this is power function. It will be powered by 1 divided by 5, yes? Because it should be n minus 1 root, okay? Result is again relative number, yes, mean growth coefficient. It is higher than 1, yes. It is mean increasing. Production grows by 4.6% each year, yes. Every year you produce more gas, more by 4.6%, yes. The result will be below 1. It will be average decrease, but we have increase. And the last, calculate arithmetical mean of this flow time series, because this is simple flow time series. We can calculate simple mean, yes. Okay, we know that every year, yes, we know that every year has different number of working days, yes. I don't know how many working days, yes, were in year 1980. I know only from old calendars that year 1980, yes, had 366 days, yes. Year 1981, 365 days, yes, etc., etc. Again, year 1984 had 366 days, yes. But we will not consider this because I don't know exactly how many working days, yes, we had in these years. So we will calculate just simple mean, yes. Simple mean, arithmetical mean of this flow time series. In your formulas, you can see the first formula, yes, summation of all values divided by n. So in our situation, equal sign, sum, yes, it's all the numbers in a range of cells, summation of these values. divided by 6. Yes. So we can interpret this like average production of gas. Yes. Average production of gas 1453 cubic meters. Yes. Simple arithmetical mean of this time series. Okay, that's all. You talked about decomposition, yes? With Mr. Hellman, you talked about decomposition of the time series, and you know that the time series y in time t can be decomposed to trend in time t, seasonality in time t, macroeconomic cycle in time t, and some residual component. But this is enough for this time. So what is here? Trend. Yes, trend. Seasonality. Macroeconomic cycle. Yes. Okay, so trend, seasonality, and macroeconomic cycle. What is it? Trend. Yes, trend is a long-term development of the time series. Yes, long-term development in the time series. Trend is increasing, trend is decreasing, trend is parabolical, trend is exponential. Yes, trend has this shape, saturation, S-curve. Yes, so some long-term development which can be modeled. Yes, which can be estimated by simple function. Yes, regression line, regression parabola, exponential regression, etc. So some long-term development in the time series. Yes, seasonality. Seasonality is a periodical fluctuation. Periodical fluctuation around the trend. Yes, periodical fluctuations around the trend. So there is trend, and according to changing of seasons. Yes. For example, spring, summer, autumn, winter, yes, or months is January, February, March, April, etc. Seasonality, yes. So we can see, we can observe periodical periodical changes, periodical fluctuations, yes, periodical fluctuations around the trend, yes, which can be observed. Yes, which can be observed almost in the same way every year. Yes, almost in the same strength, in the same power every year because of changing of seasons. Yes, so periodical fluctuation around the trend. Yes, periodical fluctuation around the trend. What is it? Macroeconomic cycle. Changing of expansion and recession. Yes, in macroeconomy, in Czech Republic, in the world, in Europe. Yes, macroeconomic cycle, changing of phases, expansion and recession. Yes, you can imagine the development of gross domestic product or wages. Yes, long-term development of increasing, yes, and crisis. Yes, so changing the development of expansion and recession. Yes, it's complicated to model, to estimate this macroeconomic cycle only in one-way equation. Yes, so I will see if this will be topic of our seminars. But trend and seasonality, it's easy. We are able to model the trend. We are able to model the seasonality. So we will check our data set, yes, in Microsoft Excel, and we will draw some charts. So this is introduction to decomposition of time series. Mr. Hellman talked to you that you have additive decomposition and multiplicative decomposition. Yes, trend in time t and seasonality in time t and macroeconomic cycle in time t. Yes, multiplicative. You can imagine, for example, this development. There is the trend, yes, and seasonality. Yes, has this development. Yes, the variance, the variation of changes. Yes, is changing. Yes, then we have changing of development, increasing variance in the time. So it's possible to use this multiplicative decomposition. So okay, we will check the data. Okay, can you see the screen? We will use sheet number 2, which is here, and you can see we have here observations, yes, and the development of average wages. What is this? We have here observation from first quarter of year 1995 to fourth quarter of year 2012. Yeah? So this is quarterly published time series. Seasonality, yes. Seasonality can be found only in quarterly or monthly published time series. Yes, if you have annual time series, there is no seasonality, yes, because seasonality is periodic fluctuation because of changing of seasons. Yes? So we have here spring, summer, autumn, winter. Yes, and because, for example, in winter, in your wage, you can find the special bonuses. Yes, special financial bonuses. Wages are higher in winter, yes. So we will check this development of time series. You can see this column, yes, average wage. I will select this data set, this column. Yes, we have here insert button on the top of this screen. We have insert button. There we have charts. And I will select insert line or area chart. Yes, and I will select this simple line chart. Yes. Okay, so this is the chart with development of average wages. I will correct the axis because there is the time. Yes. Observation, first, second, third, fourth, etc. We have here these dates, yes. So I can click on this button, select data. Yes, you have here design, and there select the data. Yes, I will click on select the data, and there is horizontal category axis labels. Yes, horizontal category axis labels, edit. I will click on edit button, axis label range, these values, observations, yes, from the first quarter of year 1995 to fourth quarter of year 2012. Okay and okay, yes. Maybe I I will use home and 6 points. Okay, maybe this will be better. It's smaller, yes. Now it's smaller, bold. Okay. I will also correct vertical value axis, right button, format axis, bounds. I will use 5,000 Czech crowns minimum and okay, 30,000 maximum. Units, major unit 5,000. Okay, so this is development of average wages. Yes, development of average wages in the Czech Republic. You can see long-term development. Yes, increasing trend. So there is some trend. Yes, which is increasing, and these changes. Yes, these changes which are very clearly visible. Yes. Are because of seasons, yes, spring, summer, autumn, winter, Christmas period, bonuses, yes. So you can see the seasonality, and I selected the time series about the development of average wages, where you have year 2008. 2008, and you know that there was a recession. Yes, on the end of year 2008 there was recession, and you can see that the trend started to decrease. Yes, after year 2008 the trend started to decrease. But it's not easy to model macroeconomic cycle, yes, the changing of expansion and recession after, for example, year 2008, yes. So we will talk about this later. So until this moment, I think that this is all right. You can see trend, you can see seasonality. We can observe the changing point, yes, where probably started macroeconomic crisis. It's possible to add trend function, yes, right button. You can click on right. You can click by right button on this curve. Add trend line, yes, linear, yes, linear trend. You can see this trend function, and you can see after year 2008, yeah, the trend changed. The development is not increasing so much, yes, like before crisis. And seasonality will be modeled by appropriate technique. So I think that this will be enough for today. This was 5th seminar of our academic semester. I hope that school will be still open, at least for employees. So I hope that I will provide to you another video seminar next week. Yes, video seminar number 6. So that's all for today. I hope that you don't have any question. I hope that everything is clear. So I wish you good luck, nice day, and I hope that I will see you next week. So bye bye.